Hello everyone, welcome to another video from the tutorial series Aspen Plus Mastery and Certification. My name is Tabish. Today we will discuss property methods used by Aspen Physical Property System for the estimation of different thermophysical properties, explore the method assistant tool that is used for the selection of appropriate property method, and view different indirection parameters. Before moving to the tutorial, let's have a brief background about the property methods. Choosing the appropriate property method is often the key decision in determining the accuracy of the simulation results. The properties that Aspen Plus estimates for the process simulation can be categorized as the thermodynamic properties and the transport properties. Thermodynamic properties include the properties such as fugacity coefficient, enthalpy, entropy, Gibbs free energy, and volume, whereas the transport properties such as viscosity, thermal conductivity, diffusion coefficient, and surface tension. Aspen Physical Property System uses two terms regarding the property methods. First is the property model and the second is the property method. Before expanding the discussion, you first need to understand the difference between the property models and the property methods. Property models are the mathematical relations that relate different state properties with the system variables or to state properties through fundamental property relations in order to eliminate the need of measuring all the properties of the system in different thermodynamic states. Whereas the property method is a collection of different methods and property models that Aspen Plus uses to compute the thermodynamic and transport properties. Let's first explore property models available in Aspen Physical Property System, then we'll move on to the property methods. In Aspen Plus Help, there is a comprehensive discussion about thermophysical property methods and models. Let's move on to the models. Thermophysical models are categorized into thermodynamic property models and transport property models mainly. Some of the models that are used for the calculation of non-conventional solid properties are also listed in this. Under the section of thermodynamic property models, all the property models that are related to the thermodynamic properties are listed. Pure component equation of state models are used for the calculation of fugacity coefficient and departure functions of enthalpy, Gibbs free energy and entropy, and similarly the volume of vapor and liquid. Similarly, the mixture equation of state models are used for the calculation of all of the above properties for the mixtures using appropriate mixing rules. Following table gives a very comprehensive overview of the available equation of state models, the model name coded in Aspen Plus, applicable phase, and whether the equation of state model is applicable for the pure component or for the mixtures. You can recognize couple of equation of state models, for example, standard Planck-Robinson equation, Rayleigh-Strong equation, Sauve-Rayleigh-Strong equation that are commonly taught in the thermodynamic textbooks. The activity coefficient models are used for the calculation of activity coefficient of liquid mixtures. You can recognize couple of activity coefficient models, non-random two liquid NRTL model, Unifact model, Van Laar model, and the Wilson model. Similarly, there are some thermodynamic models for vapor pressure and liquid fugacity, heat of vaporization, heat of sublimation, molar volume and the density, heat capacity, solubility, including Henry's constant model, and few other models. You can also view the mathematical equations of these property models for your reference. For example, from the equation of state models, you can recognize the mathematical relation of standard Planck-Robinson equation, corresponding mixer rules, similarly the mathematical relation of Rayleigh-Strong equation, and also the mathematical relation of Sauve-Rayleigh-Strong equation. Likewise, the mathematical equation of activity coefficient model, including non-random to liquid NRTL model, the binary interaction parameters of NRTL model are also listed here. Similarly, the Van Laar activity coefficient model and commonly used Wilson activity coefficient model. If you are interested, I suggest to visit other model equations as well to have a very good feeling of the Aspen physical property estimation system. The relevance of the model equations for any given system and values of the coefficients that appear in these model equations are the backbone to the accuracy of the models. During the simulations, these parameter values are either retrieved from the Aspen property database, for instance, NIST Thermodata Engine. We will explore this data engine in the upcoming videos. Alternately, these parameters can be regressed using appropriate and reliable experimental data, or can be estimated from the known information, for instance the molecular structure of the components, using specialized property estimation methods and correlations. Otherwise, you can manually input the property parameter values that you can find in the external sources. Likewise, there is a range of mathematical relations representing the transport properties, including the viscosity models, thermal conductivity models, diffusion coefficient models, and surface tension models. Aspen physical property system assigns code values to the model equations in order to facilitate in the development of user-defined property method. You can see the model option codes available here. For instance, the option codes for the activity coefficient model are given on this page. In the tutorial, we will have a look on these code values. That was a very quick tour of the property models. If all these property models are well defined, then what is the property method? As discussed earlier, the property method is a collection of the methods and models. In the method specification section of Aspen Plus, we primarily define the property methods that includes a large number of sub-property methods and the property models. To better understand the concept of property method, let's consider how Aspen Plus calculates the enthalpy values. Here is the graphical representation of enthalpy calculation framework. The reference state for the enthalpy calculation in Aspen physical property system is considered as the elements at standard temperature pressure conditions. The standard temperature pressure in Aspen physical property system is set to 298.15 Kelvin and the pressure is 1 atmospheric. The enthalpy calculations follows these three steps, including standard heat of formation of the components in the ideal gas state at standard conditions. This information can be retrieved from the Aspen database, for instance Pure 40, that contains such information of more than 2000 pure components. The second step in the enthalpy calculation is the enthalpy change involving temperature change from the standard temperature pressure conditions to the system temperature but still constant gas conditions, whereas the third step involves taking the system from the ideal gas state and the system temperature to the compound at system temperature and pressure that exist in the real conditions. The enthalpy change involved in this step is termed as residual enthalpy or the enthalpy departure function. If the phase transformation also occurs, then the heat of vaporization is also determined and added during enthalpy calculations. There are a large number of thermodynamic models available that can help the estimation of enthalpy departure function, including equation of states and generalized correlations. So the Aspen physical property system has to define a set of models from the pool of large number of available models to determine the enthalpy of the component or the system at given conditions. Similarly, Aspen property system has to define a unique set of model equations for the given system out of the pool of models to estimate other thermodynamic and transport properties. Such collection of model equations for specific system is termed as the property method. Now consider the complexity of the real systems and their stringent operating regimes. It is a very intellectual job to define a property method without in-depth knowledge of the thermodynamics and transport subjects. Therefore, Aspen Plus includes a considerable number of built-in property methods that are sufficient for most of the applications, and you must select one or more property methods to model the properties of the specific system in your flowsheets. For further assistance, Aspen has developed a pretty decent method assistant tool to help you select an appropriate built-in property method. You can create a new property method to suit your simulation needs. For beginners or for the specific application, built-in property methods of Aspen physical property system can serve as an excellent job since they are tuned very nicely. And if you are a research student, then you need to be fully aware of the nature of the system and relevant property models to develop an appropriate property method. Aspen Plus has made it open to view and modify the property models under property method section to fulfill your needs. Let's consider following case study to understand the property methods and seeking the help from the method assistant tool in order to define a specific property method. In the given case study, consider an equimolar mixture of the water and ethanol that enters the system at 2 bar pressure. You are aware that water and ethanol mixture is highly non-ideal mixture in nature and forms the azeotropic mixture. So you are asked to define an appropriate property method to simulate this system, view the calculation routes for thermodynamic properties such as fugacity coefficient, and view different interaction parameters for the estimation of activity coefficient from the available sources. So let's dive into the Aspen Plus and solve this example. Let's start a new simulation without selecting any template. Enter components as water and the second component is ethanol. Once you are done with defining the components, go to the next input from here, or you can browse the navigation pane. In the method specification section, here you need to define the property method. What are different property methods that have been developed by Aspen Plus? Here is a comprehensive list of the methods that are developed for different process applications. And these methods are grouped into couple of categories. You can filter the methods based on the process application, for example, biomass conversion processes or general chemical processes or coal processing, electrolysis process, or the methods related to the environmental applications and so on. Just to see what are different methods that are applicable for water and steam systems, here is a list of 4 property methods. For chemical processing, choose the category chemical. Here are all the property methods that are applicable for the chemical processing. As you can notice, most of these methods are based on the activity coefficient models. Some of them are based on equation of state models, and even the combination of activity coefficient and equation of states. Still, it's not very obvious to choose a specific property method from the list of a large number of available methods. To narrow down the selection, you can use the method assistant tool that is specifically developed for the assistants to select the appropriate method either based on the known information of the component type or the information of the process type. For given example of water and ethanol system operating at 2 bar pressure, let's proceed to methods assistant. Either go to specify component type or specify process type. Let's proceed to specify component type. We have a system that is composed of the chemical processing, so we can choose the chemical systems. Other available options are the hydrocarbon systems, special components including water or amines or sour systems or sour water system or carboxylic acids, hydrogen fluoride or electrolytes, and also the category of refrigerants. For chemical systems, you need to specify whether the process is operating below 10 bar pressure or above 10 bar pressure. In the given example, the system is operating at below 10 bar pressure, so go to the next window. Aspen has suggested property methods that are based on the activity coefficient methods, including NRTL, UniQuac, or UniFac. While using these activity coefficient based property methods, you need to consider following issues. In case the system is operating at above 10 bar pressure, method assistant has suggested equation of state based methods including advanced mixing rules such as SR polar, PRWS, RKSWS, and so on. For further details about these methods, you can also scroll to the help. So let's see how you can use method assistant based on the information about the process type. Go to specify process type. Here is the list of process applications that are commonly involved in the chemical process industry. In case if you are working with the electrolyte systems, the method assistant has suggestion of using electrolyte NRTL with RK equation of state. Alternatively, there is a method ENRTL-SR or the generalized correlation specifically tuned for the electrolyte systems. Similarly, for the petrochemical industry, there is a wide range of available property methods based on the equation of state and activity coefficient based methods. This is how you can use the method assistant tool to select an appropriate property method from a list of a large number of available methods. So for the given system, let's choose NRTL method. What exactly this NRTL method is? Go to the selected methods. Here you can see the method routes and the property models. These are the models selected for the NRTL method for the estimation of corresponding thermophysical property. For instance, the Fogarty coefficient of the component in the gas mixture is estimated by ideal gas equation of state model for the NRTL method. Similarly, the liquid phase activity coefficient is estimated by NRTL model itself. The liquid pure component vapor pressure is estimated by general models for the pure liquid vapor pressure. For instance, extended Entropy equation, Wagner equation, and NI25 equation, and so on. Similarly, vapor mixture molar enthalpy departure is also estimated by ideal gas equation of state model. So you can notice that most of the properties are estimated by ideal gas equation of state in the NRTL method. If you are interested to see how the other methods are composed of, you can browse to the intended method and see the details of the composition of the method. For instance, NRTL RK method. The Fogarty coefficient of component in the vapor mixture is estimated by Rutledge-Phong equation of state model instead of ideal gas equation of state model as for the NRTL method itself. So go back to the previous NRTL method. Even for the NRTL method, you can change the selection of the appropriate model for the given thermophysical property. For instance, if the ideal gas equation of state model is not appropriate, you can change the model from this drop-down list. You can see there is a range of available property models that are available for the estimation of a Fogarty coefficient of a component. You can browse other properties and corresponding property model as selected by the NRTL method. What are different properties that are affected by the activity coefficient model? You can see from this affected properties. So in total, 4 properties are dependent on the estimation of the activity coefficient, including liquid Fogarty coefficient, liquid mixture molar enthalpy, and liquid mixture molar entropy. Because of the selection of inappropriate model for the estimation of activity coefficient, you can forecast that these properties will be affected as well. So these are all the individual property models used for the estimation of the corresponding properties. So you can see the details of the property estimation method in the property routes. Here property routes are defined, including whether you are interested in viewing and modifying the property routes of pure thermodynamics, mixture thermodynamics, pure transport, or mixture transport. Similarly, if the property is the major property or the subordinate property. How the liquid Fogarty coefficient of a component in the mixture is estimated. You can see the property route from the view button. This is a complete hierarchy of the estimation of liquid Fogarty coefficient. For the NRTL method, liquid Fogarty coefficient is calculated using Henry's law, ideal gas law, NRTL model, and extended Entropy equation model. You can also consult the help to view the details how the liquid Fogarty coefficient is calculated. Let's go to the help button. Here you can browse the details of the estimation of liquid Fogarty coefficient. So the estimation of Fogarty coefficient of a component in the liquid mixture is related to the activity coefficient, Fogarty coefficient of the component in the vapor phase, and the vapor pressure. So in order to estimate the liquid component Fogarty coefficient, you have to have the estimation of activity coefficient, vapor pressure, and pure component Fogarty coefficient in the vapor phase. And all of these 3 components of this method have a list of available property models. Therefore, how this liquid phase Fogarty coefficient is estimated for the NRTL method, you can view the route from here. The activity coefficient is estimated by NRTL model, and for the mixing and 3 component mixing rules, weighting factors are used. The vapor pressure is estimated from the general vapor pressure models. The Fogarty coefficient on the vapor phase is estimated by the ideal gas equation of state model. Even the ideal Poynting correction is also used, and by default for the NRTL method, the calculated Poynting correction is set to unity. For the non-condensable gases, the Henry's constants are calculated using Henry's model without any pressure correction. Even if the pressure correction is required, the correction factor for the NRTL method is set to unity. So this is how you can browse how a specific property is estimated when it depends on other thermophysical properties. Similarly, if you are required, you can edit the property route as well. You can view the route details as well as the routes for the individual property. Here are the option codes that we discussed in the background. If any property has multiple available methods and possible multiple combinations, then we can specify the combinations using option codes. For instance, the option codes for the Henry's constant mixing rule weighting factor are set to 3 and 0. You can consult the help about the possible option codes and the way how these codes define the subordinate property models, and none of the available property methods for the estimation of liquid Fogarty coefficient is appropriate for your selection, then you can create the property method just for the liquid Fogarty coefficient by yourself as well. Once you are okay with the selected method and corresponding property models, then you can proceed to the interaction parameters. Since you are asked to view the binary interaction parameters of activity coefficient, you can go to NRTL under binary interaction parameters. Interaction parameters for the estimation of activity coefficient in the NRTL methods are listed. For the water ethanol combination, when water is considered as ith component and ethanol is considered as jth component, you can view different sources from where you can browse the binary interaction parameters. For instance, the current information is taken from VLE-IG. Other available sources include VLE-RK, VLE-HOC, and so on. These are different sources that store the information of binary interaction parameters of water ethanol mixture for the estimation of activity coefficient. In order to understand what are these values and where are they used, you can go to the help to view the mathematical relationship of activity coefficient by NRTL model. As you can see, the activity coefficient of ith component gamma is related to several parameters. The binary interaction parameters include A, B, C, D, E, F with a subscript ij representing the combination ith component and jth component. You can browse the below table. Here aij symbol correspond to the first entry termed as the element 1, and the last two entries that are T lower and T upper are the limits of the temperatures under which those values are applicable. So the value 3.4578 is the first element of this entry, and this value is used in the activity coefficient estimation, specifically for the estimation of parameter tau ij. Of the use of these parameter values with respect to temperature, and these limits are 24.99 to 100 degrees Celsius for the current entries. If you are operating beyond these temperature limits, you can check other available data sources as well. For instance, NIST IG. You have different values stored for this combination in NIST IG source, and the temperature limits for this source is minus 51.3 degrees Celsius to 200 degrees Celsius. It is also possible that none of these values are exactly meeting your requirements. Then you have the option to regress the binary interaction parameters using appropriate experimental data. Similarly, you can also view the parameters for the pure component property estimations, including heat capacity, thermal conductivity, vapor pressure, and so on. For instance, what are the parameter values used for the estimation of heat capacity? You can notice the property parameter values for the two components, and how these parameter values are used. You can also consult the equation. Besides temperature dependent property parameters, you can also view the scalar properties as well. For further learning, I suggest to practice following problem, where a mixture of acetone, methyl ethyl ketone and hexene is provided. So you are asked to define an appropriate property method to simulate this system, view the calculation routes for Fogarty coefficient and enthalpy departure functions, and view binary interaction parameter values, available sources, and temperature limits for the Wilson activity coefficient model. So in this video, we had a detailed discussion about the background of property methods, difference between property methods and property models, how to select an appropriate property method using method assistant tool, and view the binary interaction parameter sources, parameter values, and corresponding application limits. In the next video, we will explore NIST thermodata engine, retrieve the parametric values, and perform property analysis of the pure component, binary mixtures, and the tertiary mixtures.